Okay, good afternoon, guys. So, um, let's see. I want to do today. Um, First, if you have any questions about the fourth assignment, we can talk about that a little bit. But if you don't, it's okay. We'll talk about it on Wednesday. So there's that. Other than that, we've been building up. We've been building up everything. We built up the integers loosely, and we'll say a little bit about the rational numbers as well. And then we'll say, okay, so here's our plan. We started talking about sets at the beginning. You constructed the natural numbers. Okay. Again, roughly those live inside the set of rational numbers. Okay. And those live inside the set of complex numbers. And that's pretty much where we are going to stop, more or less. Okay. After we construct the real numbers, we'll talk about things like cardinality and other things. Okay. And each of these successive things like solves a problem. Well, okay, we construct the integers because we want to subtract. We construct the rationals because we want to divide. And we construct the reals. We'll see exact next week, but basically we want every bounded set to have a least upper bound. And we construct the real numbers so that they do have that property. In other words, we construct the real numbers so that they are a complete field, and they are still just like all the things that came before. Okay. So here's our progress. We've done that. We're kind of halfway through that, and then we have to do this. We have to do this. Okay. So now I want to ask, does anyone fourth assignment? Oh, someone has a question. Can I change? I can. That's not a problem. Okay. Okay. So if you have a chance, try to questions on assignment 4. Okay, for now, we're just going to move on and finish the questions before Wednesday. That is can only be good. So basically, let me remind you where we were at. We defined S to be the set of ordered pairs of natural numbers. And then we defined an equivalence relation. Just basically, two integers are the same if they represent. Well, we have to find a way to represent a difference using addition. So we just like move all the. So in our mind, but remembering that there's no such thing as 3 minus 5 in the natural numbers, we have to move like all the minus signs over. So we just say like a plus b prime equals two integers are the same if we have this equation. And this is going to be the same strategy to construct the rational numbers. pretty much the same. Addition and multiplication of integers, keeping in mind what an integer represents a difference, so you define z modulo this squiggle relation. You define addition and multiplication on z. You define the positive integers, z plus, to be the set of those okay. In order for this to be well defined, you need to show that a requirement for this is that you need to show that if mn and m prime n prime are the same, then n bigger than n if and only if m prime bigger than n prime. Because you need to show that an integer, like for any representative of the integer, the first thing is bigger than the second thing. Okay, and then you can show, well, then you can show that the set of integers equals the positive integers union 0, the integer 0 union minus the set of and the union is disjoint. Okay, then what you would do, I mean, we're not going to do it, but what you could do is then define for A and B and Z, define the rule that A is bigger than B if and only if A minus B is a positive integer. Then you can prove all your favorite. There are many of them, so I won't write any of them down. Okay, but you get a theorem. You get that Z, you get less than on Z is a linear order. And one is a partial order, meaning, I guess I should put less than or equal to. So it's a partial order, meaning it's reflexive and such that any two elements of Z are comparable. Okay. Then another thing you can prove is that AB equals 0 implies A equals 0 or B equals 0. Okay. I just want to spend all the things we need to develop to prove that. Okay. So we'll call it a proof, but in quotation marks. So let A and B be two integers. Suppose A times B equals 0. Now let's see what that means. First of all, the number 0, or the 0 is supposed to represent a difference of natural numbers. So 0 is an equivalence class of ordered pairs of natural numbers, and it's just like the 0. So the two natural numbers are always going to be the same. So this is the equivalence class of 0. Or sorry, yeah, this is what the integer 0 represents. So each of these is each ordered pair has different 0. Okay, so that is the integer 0. Okay. So A is a set of ordered pairs. So write A to maybe be represented by Mn, and B is going to be represented by UV, say. Now A times B roughly is just M minus N to get Mu plus NV minus NU plus MV. So this is okay, and if this equals 0, it means V. Oh, the right, sorry. Move this, and then okay. Okay, now the problem is to like solve this equation. And what we want to show is that either M equals, and we have this equation. So roughly how we do it would be, suppose for a contradiction that M is strictly bigger than N and U is strictly bigger than V. Okay, and what could we do? And MU plus NV would be strict, like, here's, I guess, I'm not sure where this goes, but strictly bigger than NU plus NV, which is NU plus V. Anyways, I guess I don't want to get or something, I guess. If we were solving it in the integers, we could do it, we do like gather the N's and the M's. We'd write MU minus V equals N. Equals NV minus U or something. And unless U equals V, like this is a positive number and this is a negative number. So we could use prove something about this equation. Okay. but we don't want to, I don't want to do that now. But anyways, like once you get this equation, this is like some problem stated in the like language of natural numbers that you can solve. And then once you prove, okay. Okay. And then from things like that, you'd prove, like assuming all the natural arithmetic properties of the natural numbers, you'd prove the same for the integers. Okay. Thing, except now our problem is that, you know, it doesn't take too long for students to get introduced to fractions. But yet here we are, we need to construct them rigorously now. Okay, so we need to have a thing like 3/5. Okay, so define U to be the order pairs of integers. In other words, we're basically defining U to be the expressions like A over B. Okay, and define, I used squiggle before, so I'll define squiggle for on U. We'll define it by, like rational number as A prime B prime, if and only if. Now I need to write an equation in integers. Well, we need for this is just like cross multiplication. Right? Because we want these to be like fractions. So these should represent the same fraction if they represent, we're taking A over B equals A prime over B prime. Well, if and only if AB prime equals A prime B. Okay. And then you want to define, and then we define the rational numbers just to be the integers modulo this equivalence relation, which I did not even show it was an equivalence relation. But you can imagine if it wasn't an equivalence relation, this would cause big problems in elementary school. Okay. Okay, so we've defined the natural numbers just by unraveling like the regular rules for addition and multiplication of rational numbers and expressing them in terms of integer arithmetic. Because remember, we're trying to, like this, the point of this, we're trying only the properties of integer arithmetic, like the fact that you can, you have the division, but you need to invent something like 3/5. Okay. So of course, we should all be able to add like 3/5 plus, plus 1/7, and we're just trying to rigorously do that. Okay, so the next, A over B plus A prime over B prime, just to be AB prime plus A prime B divided by BB prime. And then you'd have to do things like show that this definition is representative of this rational number and this rational number. Okay. Then you have to define multiplication. And well, it's just how you should do it. But not only that, you also have to define, like, for example, you can define, so if A and B is non-zero, you define the reciprocal to just be B over A. And everything good like that. You define the integers as a subset of rational numbers by defining a injective function to the rational numbers. So you take an integer a, and you just represent it as the fraction a over 1. Okay. Then phi is 1 to 1 and identifies like the integers as a subset of the rational numbers. Sorry, I went over too far again. And then to be really careful, you'd have to show that like that kind of stuff, but okay. Then you would define the positive rationals. Well, the positive by like the number, like the integers where the numerator and denominator are both positive. So Q plus is just those a over b such that that allows you to define positive rational numbers, which allows you to define less than, define a over b less than c over d if and only if c over d minus a over b is a positive rational number. Okay. Then we just have the following, like we could state the following theorems. Theorem. The rational numbers are a field. Q is a field. 2. Q is linearly ordered. Okay. And, you know, for many things, that's kind of good enough. Okay, but oh, let's see. So there is something missing. The problem is that when you, or what is our problem? We want to represent the rationals on a number line. But there's actually like kind of holes in it. There's missing stuff. And what's an example of something missing? We have the square root of 2 is missing. Okay. No, the square root of 2 is like kind of like not some outlandish thing. For it not to be a number is kind of like will cause us to go, we can draw a triangle with right triangle with ones on the two sides, and then whoops, this length is not even a number. Well, that's kind of a problem. So so we need to fix that. So let's take a break for 5 minutes again, and then when we come back, we'll discuss this problem more.